Okay, in this example, we are looking at the formation of aluminum from aluminum oxide, which is found in bauxite. And I'm going to go ahead and record these videos, and they take up a lot of space in the PowerPoint show, so I may post them separately and also post a PowerPoint show without the videos, because I'm finding with my advanced class that these videos take up a lot of space and take a long time to download. So I'm working on both methods, and hopefully we can decide on one. Okay, in this example, we're being asked about aluminum produced in this way, and we're given delta H is 1676 kilojoules per mole. That means that heat is a reactant. We know that because delta H is positive. So if aluminum is produced in this way, which it usually is not, how many grams of aluminum can form when 1 times 10 to the third kilojoules of heat is transferred? Okay, so we are told that if we are using 1 mole of aluminum oxide, that it requires 1676 kilojoules of energy input for every 1 mole of aluminum oxide that is used as a reactant. This number up here is often going to be the conversion factor you're going to need to get from heat to amount of substance. In this example, we also are going to end up needing to know the molar mass of aluminum, which is 26.98 grams of aluminum per 1 mole of aluminum. And then, because we're starting out with the aluminum oxide, that is related to the amount of heat. So that's here in our denominator. And we want to end up with aluminum. We have to use the stoichiometry in the reaction to get from one to the other. So I'm also going to write down a conversion factor for that. So for every 2 moles of aluminum we make, we need 1 mole of aluminum oxide to react. Okay, so I'm interested in ending up with mass of aluminum. So that is going to be this, is what I want to end up with. So I'm going to have that on the top. And I'm going to go ahead and start out my dimensional analysis with that on the top. That ensures that you're not going to end up with your answer flipped over. Now, some of you, I know, like to start out in a different way. So some of you might want to start with this, and that's totally fine. If you do start with this, though, you have to know that you're going to have to flip it over when you start. And that is not intuitive sometimes for people. So I've taught you last semester to start with the thing you want to end up with and put it on the top. So that's how I'm doing it. But because I'm multiplying all of these together, you can do them in any order. So if you want to start here, that's totally fine also. Okay. So I need to get rid of moles of aluminum on the bottom, and I also need to at some point use this, which has aluminum oxide in it. So it makes sense at this point to go ahead and get from aluminum to aluminum oxide. So now I've used this and I've used this, and now you can see I'm going to put in my my conversion factor that has my delta H in it, and I can see now that I have to flip it over. So that became obvious because I needed to cancel moles. So that's going to give me kilojoules on the bottom. Notice that I haven't used this number yet. And I know I need to use that here because if I stop right here, what do I have? Of grams of aluminum produced per kilojoule of energy. But in this example, I don't have 1 kilojoule, I have 1,000 kilojoules. So I'm going to multiply by 1,000 kilojoules. So you could actually have listed that over here as part of the list of things you want to include in your dimensional analysis. So that's going to get canceled out, and I put an equal sign. This gives me 32.20 grams of aluminum. Now if we go back and look at our significant figures, these numbers that are coefficients are exact numbers. They don't limit our significant figures. Here I have 4, here I have 4, here I have 4, so I'm going to have 4 in my answer. So I need to keep that 0 on the end. And that is the final answer.